Last Sunday, Intel introduced a new line of CPUs named Ivy Bridge. There's been a lot of discussion and buzz surrounding Ivy Bridge, but some of that discussion has been very technically involved. So, in the next couple of minutes or so, we are going to discuss in simple terms what is so important about Ivy Bridge and who this new range of CPUs is targeted at. Ivy Bridge is based on the Sandy Bridge architecture. This means that the building blocks that make up both lines of CPUs are very similar, and you can see that here. For example, the actual arrangement of the cores, the shared L3 cache, and even the memory controller are very similar. The most significant difference, which is not so easy to see however, is the size of the transistors. The size of the transistors in a CPU is very important because there are two basic ways to make a CPU faster. Either speed up the transistor or add more transistors by making them smaller. Pushing up the speed, however, is like revving up your car engine. There is a limit to how far you can push a car engine, and it will always produce more heat. The same goes for CPUs. Heat is a real issue with CPUs because processors are being pushed into smaller and smaller cases, so getting rid of that heat can become a real problem. That leaves shrinking the transistor, and that is exactly what is so special about Ivy Bridge. The transistors in Ivy Bridge are 30% smaller than the transistors in Sandy Bridge, and, as we are going to show in this video produced by Intel, this is where the real technological breakthrough is. This is a single Sandy Bridge transistor. A transistor is really the same as a switch. These yellow dots over here represent the current flow when the switch is closed. The challenge with making very small switches, which are very close together, is that as the switches or transistors become smaller and more tightly packed together, the current meant for one transistor will leak to another transistor, and this will cause a computer to freeze or blue screen. This happens because electric current, like water, will always follow the path of least resistance. What Intel has done to combat this is to introduce what is called a tri-gate transistor. It's called tri-gate because whereas previously there was one path that the current flowed down, as you can see here in the Sandy Bridge transistor, in a tri-gate transistor, as you can see here, there are three paths that the current can flow down. 1, 2, and another one on the other side here. In other words, a tri-gate transistor significantly widens the path the current flows down so that the current stays on track and does not leak to an adjacent transistor. Now, this is extremely significant because the smaller the transistor, the less power the CPU consumes, and the more transistors you can fit in a given space, so the greater the processing power of that CPU. And that's exactly what we see in this graph here. This graph shows the time taken for different CPUs to transcode the same 5.95 gigabyte file. When we tested the Ivy Bridge i7-3770, represented by bar 7 here, against a Sandy Bridge i7-2700, represented by bar 8 here, the Ivy Bridge CPU was about 10% faster while consuming 20% less power. The real technological breakthrough for Ivy Bridge, however, is that it opens the way to smaller transistor size with lower power requirements but increasing CPU processing power. So who is this CPU aimed at? Well, as you can see in this graph, in highly multi-threaded applications, it's still not quite as fast as the 6-core CPUs with the Sandy Bridge architecture, or in fact, even the Nehalem architecture. So for applications which are highly multi-threaded, such as video rendering and transcoding, the number of cores is still more important than speed. But for applications which are not highly multi-threaded, such as editing photographs and gaming, the new Ivy Bridge CPUs are second to none.